a researcher, an educator, and an icon in the IT industry. I have known Laura's name probably since the 80s, actually. She actually worked for Novell in the 80s, and I think that may have been where I first met her. She is a phenomenon par excellence. She is unbelievable, and you do not know how fortunate you are to listen to her today. She's best known as the founder for Chapel University, Wireshark University, and the WCNA certification program. You will see that she is highly energetic. You don't have to really have me tell you that. She's authored a lot of books, industry titles, all sorts of things. She's presented to thousands of people, and she has led a 100% virtual conference. In fact, Close It was on the books before COVID hit. Very, very cool, Laura. She's also going to be a keynoter for our High Tech Transformed, which is the National Science Foundation conference that would have been in Portland this year, but it won't be. And she's going to be presenting from there on how we might be able to offer workshops and conferences online. She's going to give us tips and tricks. And we're delighted to have you, Laura. I'm going to turn it over to you. Thank you.
All right, so welcome everyone. And I'm glad you could join me. This is a relatively short version of this presentation, but this presentation focuses on the interplanetary internet, or IPN as we call it. I'm showing the letters IPN in lowercase because when we do addressing for the interplanetary internet, we use lowercase IPN in front of the actual address. So I have a handout for this session that I will work with Anne and Mark to ensure all of you get. It is a file that contains my slide set. All right, so the handout for this will include the slide set that I'm going to show you here. That slide set is fully annotated, so you can look down and see in the notes section information about each slide. I also have a quick reference sheet that I will talk about in just a moment when we go and look at the Deep Space Network. And I also have trace files of interplanetary communications to show you. So let's go ahead and just jump into it because, only 30 minutes. First of all, why do we need this communication system, and what kinds of challenges are we facing when doing something like this? And as an example, I'm going to take the New Horizons spacecraft. Now, the New Horizons spacecraft was launched. So first of all, when the New Horizons spaceship left the Earth, its primary purpose was to do a close flyby of Pluto. And as it did this close flyby, and the purpose was to find out about not only Pluto, but also the moons of Pluto. We weren't exactly sure how many moons there were when this particular spacecraft left the Earth, but it was to do this close flyby of Pluto. What's interesting about that particular mission is that as it's doing its close flyby of Pluto and it's sending back to Earth these images, when it's farther away from the target, of course, the images are smaller and the files are smaller. We've got to get those files from that spacecraft down to Earth. So we have to have a way to have a communication system. Not only that, but after the flyby of Pluto occurred, that spacecraft still had enough power that it could continue along beyond what its original mission was. So NASA decided, look, we're going to go ahead and we're going to send commands up to the spacecraft to tell it to go explore an object out in the Kuiper Belt. Now, this object is originally called 2014 MU69, and it is out in the Kuiper Belt past Pluto. Pluto is one of the objects within the Kuiper Belt, but this MU69 was way out there beyond Pluto. If you think about what it takes to get this stuff down, this object, this MU69, which eventually got renamed to Ultima Thule, and then got renamed again to Ericoth. It is now called Ericoth. It's 4 billion miles away from Earth. So when we talk about networking in the terrestrial environment and round trip times, and we talk about delays, it's nothing compared to what we have here. So the data path one way, when New Horizons was doing its close flyby of Ericoth, the data path one way is over 6 hours. So we've got to get that data down. And as New Horizons gets closer to Ericoth, the images become much more well-defined, more granular, but the file sizes. So we've got to get a way to get these images down. Now, this animation that you're seeing here was created from the images that were sent back for the flyby of Pluto. And you can see that early in the process, when Pluto was pretty far away from New Horizons, I mean, right at this point, this is not going to be a huge file to get down from the spacecraft down to the Earth station. But as it gets closer and closer and closer, you can see the resolution is getting higher. And as the resolution gets higher, this file gets larger. So we've got to get this down to Earth. This is what the original view was of what became known as Ericoth. So this is an image that was taken by the Hubble spacecraft. There was even an earlier name than MU-69 for this Ericoth, this object out in the Kuiper Belt. And this is the number up on top, PT1 111-0-113Y. And this is actually from a NASA slide set where they were going through and deciding what to do with New Horizons after it finished its flyby of Pluto. They literally picked Ericoth from this image here, which just sounds crazy, but that is true. As New Horizons left its flyby of Pluto, it headed out towards what is now known as Ericoth. This is the image that it sent down on August 16th of 2018. It was January of last year where the spaceship was going to finally get close enough to give us a real solid detail of what this object was going to be. And at that time, it was nicknamed Ultima Thule. So this was one of the first images sent down as New Horizons started to get closer. The two images that you see on the left were released on January 2nd and then January 3rd. And what we're seeing is that Ultima Thule was a contact binary, two individual objects in space that began to spin around each other very slowly, not quickly, but very slowly, and they fused together. And that's why people called it Ultima Thule. They gave it the double names there. They called the bottom one Ultima, the top one Thule, but we don't use those names anymore. We use Ericoth. Be careful of using the name Ultima Thule because there is a Nazi occultist group that uses the name Ultima Thule to refer to something, so we don't really want to use that name moving forward. Luckily, we have a new name for it, which is Ericoth. But the image that you see on the far right-hand side is a very detailed image. We don't have all the data from New Horizons flyby yet. So it still is sending data down to us on Earth now. So when we talk about spacecraft or landers or orbiters or probes needing to communicate these images down to Earth, and the fact that we need to communicate commands to control those spacecraft, orbiters, landers, probes, we have three needs that we need to address here. First of all, we need to deal with the transmit capability. And when we talk about that, we're talking about transmitting to Earth. Most data goes from interstellar space to Earth. Those are the images that we're getting. That's the scientific data we're getting on soil samples or atmospheric samples and things like that. And one of the big advancements that's come up are these CubeSats. So we'll talk about what these CubeSats are. They are cube satellites. The next thing is on Earth, we need to consider our receive ability. How do we receive these signals coming in, these radio frequency signals coming in? This was solved through the Deep Space Network, or DSN. And in a moment, we're going to go out to the DSN right now, and we're going to go live, and I'm going to show you which one of the spacecrafts we are currently communicating with. And I hope there's one of them that is active right now, but we'll take a look and see what's going on right at this moment. And then finally, the third piece is, if we've got a way to transmit the information down to Earth, and on Earth we have the Deep Space Network, which is able to receive that information, we've got to think about the relay system to get that data down to us. If you look at a spacecraft out and perhaps orbiting, let's say the Mars Reconnaissance Orbiter, which is orbiting Mars right now, there are times when that spacecraft is on the opposite side of Mars. So we don't have a line of sight from the Earth. At that time, it cannot send its data directly to us. So we need a relay system to get it down to Earth. And this is where the delay and disruption tolerant networking comes into play. This is called DTN. So we have CubeSats to send it to us. We have DSN, Deep Space Network, to receive it. And then we have DTN that sits between the two of them to help us get this information down. So let's talk about CubeSats and the first time CubeSats started to get used. If you're familiar with the InSight Lander project, that was one of the times when CubeSats were used. Before CubeSats, we had the Mars Reconnaissance Orbiter, which is still active today. Who knows, in a moment we might find that we are talking to the Mars Reconnaissance Orbiter when we look at the Deep Space Network. But the Mars Reconnaissance Orbiter has some issues with it. It was launched back in 2005, so the technology was quite old compared to what we have today. It has, up until CubeSats came along, it has been relaying information about the surface of Mars to us on Earth, but it cannot simultaneously transmit and receive. So if data about an image of a crater on Mars is coming down, the folks at NASA can't be sending up commands to that Mars Reconnaissance Orbiter telling it what we want it to do next. We have to wait until the data dump happens, and then we can send the next command set up. It's asynchronous. It's very slow and sort of bulky to do that. So let's take the whole InSight landing project and why Mars Reconnaissance Orbiter wasn't the best way to get data down about the InSight lander. When the InSight lander landed on the surface of Mars, on Earth, we want to know that the landing was successful. Before CubeSats, what would have happened is a UHF frequency signal would have been sent up to the Mars Reconnaissance Orbiter, which would have to be within range to receive that. And because of where the Mars InSight lander landed, backside of Mars, so it wasn't within line of sight from Earth. So it was going around in an orbit, and there's a 6-hour blackout time before it would be able to tell us on Earth that the InSight lander successfully landed on the surface, and it deployed its solar panels and things like that. We would have to wait 6 hours for that. So this is where CubeSats come into play. When the InSight lander was launched, it was launched using an Atlas rocket, and on the back of the Centaur Stage 2, which the rocket has fallen away, the rocket to get it out into space, on the bottom of the Centaur Stage 2, there were 2 little boxes there that were about the size of a briefcase. These boxes were the 2 CubeSats. They are called Marco A, which stands for Mars Cube 1. So the Marco stands for Mars Cube 1. And there was Marco A, which was nicknamed Eve, and there was Marco B, which was nicknamed Wally. Now, Eve, unfortunately, had a problem. Before launch, the scientists found out that Eve was blind. Eve's camera did not work, but everything else was functional about Eve, so they decided to go ahead and let Eve go on this mission. So Eve and Wally were actually strapped to the bottom of that Stage 2 vehicle. And the idea is that once the InSight lander begins its landing process, these guys are going to jettison themselves off of the stage 2 area. And they are going to turn around and watch InSight as it lands and report on what happens. So here's what these 2 CubeSats look like up close. On the left-hand side, we're looking at the top, and what you see, that yellow piece laying across the bottom there, that's the high gain reflect array antenna that communicates with Earth over K-band. And you'll see a camera there. You will see that we have the solar arrays, which fascinatingly enough, everything here is pretty much off-the-shelf kind of items there, but the solar arrays are grown as an organic material. It's very interesting. On the right-hand side, you will see that there's another antenna that is very, very small, and this is a UHF antenna. And this is only for communicating down to the InSight lander. We don't use the UHF capability to communicate all the way to Earth. We use the high gain antenna to communicate to Earth. So here's the way these were used. As the InSight lander is about to begin its descent down to the surface of Mars, CubeSat Eve and Wally are deployed out into space. They open up, they have their solar panels there. They are aligning themselves to look at the Mars InSight lander, to watch this landing system. In my image, I only have one of the CubeSats up there, but both of them were up there at the same time. When the InSight lander lands on the surface of Mars, it transmits over its own high gain antenna. It transmits to Earth this tone, this beaconing tone, which is to indicate, I made it. It takes 7 minutes for that message to make it to Earth. But what if that didn't work? We wanted to have these other satellites up there to report on the landing and tell us, you know, it's great that the InSight lander can tell us it landed, but we want to know, but did the, you know, the solar panels open up? Does it look fine? Is it in a ditch? You know, what happened to it during the landing? So at the same time the Mars InSight lander landed on the surface of Mars, it sent up via UHF signal to Marco A and Marco B, Eve and Wally. It sent up a signal to basically say, I made it. It also sent that signal over UHF to the Mars Reconnaissance Orbiter as a backup. Now we know we're not going to hear from the Mars Reconnaissance Orbiter for 6 hours, but the beauty here is that Marco A and Marco B, Eve and Wally, began immediately transmitting to Earth that it had received a signal that the InSight lander had landed, and it began sending us images of the landing location so we could immediately see, look, the solar panels opened up. Look, this is fantastic. We're able to see right away that it was a successful landing. You can see the time that it took for this transmission to come from Wally and from Eve. It's only 8 minutes and 7 seconds to receive that. That's a lot better than waiting for 6 hours. The image that you're seeing on your screen right now is a selfie. This was a selfie taken by Wally as Wally looked back at Mars. As I mentioned before, Eve was blind. The camera was not functional before Eve was launched. That was known, but Wally successfully did take a picture of Mars. What you see on the right-hand side there is the solar panel. You're seeing just a piece of the solar panel, but you are seeing Mars from a distance on Wally. After this mission, Eve and Wally, after helping us understand that the landing had worked properly, after this, they have a propellant on them. It's very much like a fire extinguisher that is on each one of them, and that is used to propel them and change their trajectory. They are now in a full orbit around the sun, and there is no other purpose for their existence. So they're just in a full orbit around the sun, having done what they needed to do. So these CubeSats are now being released with all these different spaceships going up. And at one time there was a project where a company was launching a spacecraft and they set up 20 CubeSats with it just so that they could hover around that spacecraft and show the outside angle of the spacecraft to the ground station at any one time. These are very inexpensive, relatively inexpensive to build, fast to build, and they use primarily off-the-shelf components. So the folks down at Cal Poly are helping build some of these CubeSats. So you have colleges that are involved in building CubeSats as well. So this has been tremendously successful, a much better way to get information down about our different spacecraft and probes and orbiters when they are sent up in space. Now let's talk about the receiving end of this. To receive all of this data that's coming down, the pictures and the scientific information that's being gathered, again, about the soil content on asteroids or on a planet, or to get atmospheric information, we need a way to receive this. And to receive this, we use the Deep Space Network. Now, the Deep Space Network consists of a set of parabolic antennas that are sitting in 3 different locations on the planet Earth. We have Goldstone, California, which is the primary location. We have Madrid, Spain, and then we have Canberra, Australia. And these are the 3 locations. And the reason for those locations are, from each of those locations, each of them has a 120-degree view of space. So at any moment, we have a 360-degree view of space around us just from these 3 Deep Space Network locations. The one in Goldstone, California is one of the primary ones. This is an image showing the parabolic antenna. They actually cool these antennas down to below 400 degrees to dissipate noise. It's fascinating to research what these antennas look like. This is an example of looking at what is happening on the Deep Space Network. But what I'm going to do now is I'm going to take you out live to the Deep Space Network. We're going to see what's happening right now on the Deep Space Network. So, first of all, there is a page where you can go and you can find information about the Deep Space Network. All of this will be in the handouts that will go to you. When you go to the primary location for the Deep Space Network, there is a link on the right-hand side that says DSN Now. And that DSN Now will take you out to looking at what the antennas are doing at this moment. So we're going to enter the Deep Space Network, and here we go. All right, so we have 3 different panels here. The top panel that you see is Madrid, and it's not just one antenna that sits at each of these locations. There are multiple antennas, although some of these have been retired, and you won't see them actually starting up on this screen. But we have in Madrid right now, we have one antenna. It's DSS 55, which is right now talking to OSIRIS-REx. Now, this is one of the things you'll receive from me. This is your Deep Space Network cheat sheet. And on this cheat sheet, I not only have the list of the antennas at the 3 locations globally, but more importantly, I have this table on pages 2 and pages 3, which will tell you who launched that particular object that we're talking to. We don't know from here whether it's a satellite or a probe or a lander, but who launched it, what is it, when did it launch, and what is its purpose. So I recognize the letters ORX up here, that's going to be OSIRIS-REx. When you click on one of those initials in the Deep Space Network, when you're showing this in class to students, things like that, on the right-hand side, you will see that there are 3 tabs here, 3 buttons that are available to you. And I'm just going to draw these. So you have the first button, which is to view the antenna, which is what we're doing right now. The second one is to view the spacecraft itself. And then the third one is to do a world map view, which is very much like the slide 2 slides back that I showed you. So right now I am looking at the antenna, and on the bottom portion of this, it is telling me what the range is. This is 266.72 million kilometers from Earth right now. What is the round trip time in light time to communicate with that particular spacecraft? Which antenna is it on? And then it has things like the wind speed. But here's what's important. There is a more details button at the very bottom of this window. Way down here, there's this more details button. You always want to click on that. So I'm going to click on this more details button. And now I can scroll down and I'm able to see the data rate for the communications. The image here is showing data is coming down in this wavy signal, and it's showing that data is going up. So we have bidirectional data at this time. If the data is so tiny in one direction, it may not register on the right-hand side here, but so see right now the up signal is showing that it's data, but the data rate is not even showing because it's too small. We can go a little bit further down and we'll see the down signal. So right now on OSIRIS-REx, we are getting primarily data downloaded at 599.98 kilobits per second. Now on this document, on this cheat sheet that I created, I just created this last week for you. On the second page, you'll see OSIRIS-REx. OSIRIS-REx is one of the most exciting projects we have right now. It is asteroid sampling. It is getting ready to land on an asteroid called Bennu. It was supposed to already have landed. It has not landed yet. The plan is that in October it is going to land on the asteroid. Right now it is continuing to map the asteroid and do further refinements regarding its landing location. It will stay on that asteroid and take samples of Bennu all the way up until next year, till March of 2001. And at that point, it is scheduled to do a return trip to Earth to bring the samples of the asteroid back to Earth. So this document, tells you all about the different initials and what they mean and what their purpose is. That particular spacecraft or lander was launched in 2016. Let's see, GeoTail is not that interesting. It's looking at, oh, I'm so excited. In Goldstone right now, SPP is talking down to us. So let's go hop over to SPP. Okay, SPP is the Parker Solar Probe. We are sending this probe hurtling towards the sun right now. And on those three buttons that we have on the right-hand side, I'm clicking View Spacecraft. And this is the NASA image of what that spacecraft looks like. And we can see the sun behind it. There's a beautiful image there that we're seeing. But right now, this is hurtling towards the sun. And it will go within 4 million miles of the sun. And it is reporting all of this information back to us about the sun. And it's mapping the sun. It's really a fascinating project. It is one of the ones that is on the cheat sheet on the third page. So it is considered the first space project to ever, what we call, touch the sun. Touching the sun, believe it or not, is 4 million miles from the sun. It's not actually touching it, because if it did, it wouldn't talk to us. So, so there's information about that. That space probe was released in 2018. We usually use the word probe to indicate something that is one way and it's probably going to die. So we joke about it, but a lot of the Russian space projects to Mars, they called them spacecraft and we called them probes, because they slammed into Mars and they were destroyed. They were very unsuccessful in the beginning of their attempts to land on the Mars surface. Okay, so you will see every once in a while some names will pop up as things. There's one called WIND. WIND is actually a whole set of different satellites out there that are reporting on interstellar wind conditions. We have the Mars Reconnaissance Orbiter that must have recently communicated with Canberra, antenna number 36. So we can see MRO is listed there, and I do recognize MRO is Mars Reconnaissance Orbiter. So Mars Reconnaissance Orbiter has been a very successful orbiter out in space. But this is live 24 hours a day. We are able to see which antenna is receiving or transmitting to spacecrafts, orbiters, landers, and things like that. And as a new spacecraft goes up, all of a sudden we'll start to see it communicate here to one of the 3 Deep Space Network locations. So, wow, Deep Space Network, this is very cool. In the slide set, I do have an image of this. So if you're going to present this and you're in a location where you don't have internet access, you can't show it live, at least you can kind of show what it is all about. The most exciting ones that I see when they show up all of a sudden, I gotta hurry, are Voyager 1 and Voyager 2, because they're outside of the heliosphere. I can't even talk about that anymore. You'll have to look at the details, but I mean, 13.8 billion miles away from Earth, and the power is 1/20th, it's the Voyager 1 and Voyager 2 have the power of 20 billion times weaker than a digital wristwatch, but you'll still see them showing up all of a sudden, talking to the Deep Space Network. So the Deep Space Network is our receiving side, and now there's the relay side, the whole idea of how does that scientific data make it down to these antenna on Earth. And this was started in 2007, when we're sitting there and all excited about the first iPhone that came out, and we're all upset about Vista being released. Then Cerf, the father of the internet, was creating this delay and disruption tolerant network. He created an RFC specifically focused on interplanetary communications, and it's based on TCP/IP. So for the generation coming up, a strong knowledge of TCP/IP will serve them well if they are going to go into interplanetary communications. You have to know TCP/IP well to understand how we use TCP/IP to support interplanetary communications with the Deep Space Network. Here are the problems that we have when we're addressing talking from a spacecraft to Earth. We've got intermittent connectivity, as that spacecraft may go behind the sun or a planet or something like that. Oops, sorry, let me go back there. You could have a long delay, obviously, getting from, New Horizons down to Earth. It's 6 hours one way for a standard delay. You have asymmetric data rates, which means we want to send up commands, but they're little tiny commands, but we want to send down data. We want to give all our bandwidth to the data coming down. Interesting is emergencies. If an emergency happens on a spacecraft, everything changes to transmit up commands to try to recover from what's going on. And then we have, of course, high error rates, solar flares, things like that destroy the signal as it's coming down to Earth. We also have this thing called the solar conjunction, which happens every 2 years. So if we're talking to, let's say, the Mars Reconnaissance Orbiter, or talking to InSight Lander, and they're on the other, they're out on Mars, well, every 2 years, Mars is going to be on the other side of the sun. So it is not line of sight visible to us. So because of that, we can't communicate with it. This is going to last for a couple of weeks. We've got to find a way to relay around that. And that is what the delay and disruption tolerant networking system does. It uses a store and forward technique, a one-way split horizon store and forward technique to get data to keep moving towards the desired target. It understands opportunistic context. So if you're the InSight Lander and you have a bunch of pictures to send to Earth, you basically are waiting to hear if any relay goes overhead, and if it does, you'll start sending it up to that relay. But if we know that there's data that's going to come back, we can sync that data transmit process up with the delay and disruption tolerant networking, so we can make sure that a satellite does go over at the time when the data is ready to transmit. So there isn't a wait around time to hold the data. To do this, it uses something called the bundle protocol, which is covered in RFC 5050. But that bundle protocol sits inside of the TCP/IP stack. So here's the TCP/IP stack. You got your link layer stuff. We're talking radio frequency to talk through the interplanetary internet. And then you have your network layer. It uses standard IP, IPv4, not IPv6. We have our TCP transport layer, and we have the application layer. But what we do is we take data and we put it into bundles. And those bundles are encapsulated inside of a TCP/IP packet. It is a store and forward protocol, store and forward system, so that we keep data moving towards Earth, but it can sit out on a relay out in space for days and weeks and months if there is no way for it to forward on. This bundle protocol sits as a shim between the transport layer and the application up on top. And we need one more thing in this. We need a way to connect the bundle protocol to TCP. So there's something called a TCP convergence layer that sits in there as well. There's a little tiny header when you pick up the traffic. So all together, when we put this back together, we call this the DTN protocol stack, and we combine the application layer, the bundle layer, and the TCP convergence layer together, and we just call it the DTN application layer. Standard TCP underneath that, standard IP underneath that. Here's the difference between talking between hosts on the terrestrial network on Earth and talking interplanetary. On Earth, if this client wanted to talk to this server and it wants to send data to it, the first thing the client would do is it would take the data and TCP would set a retransmission timeout value. Then that client would send that data up and the routers would forward it to the server. And upon receipt, the server would send that acknowledgement back. I'm just doing a very simple example here. And once the client gets the acknowledgement that the server received the data, the client's like, great, I don't have to hold on to that. It's made it to where it's going. Okay, interplanetary is a little different. So here's an example of the layout and network addressing for interplanetary communications. And this is based on communications to the InSight lander. On the left, you have the InSight lander on Mars. It is network 65. You have the Marco up there, either Eve or Wally. And Eve and Wally sit and they can communicate on network 65, but they can also talk on the sort of interplanetary general network out in space. And then you see that we have an Earth forwarding node on the right-hand side that can talk down to Earth, which is network 81. And that's talking down to the deep space network antenna. So we have three networks here. We have 65, which encompasses Mars. We have 49, which is general space area. And then we have 81, which is Earth, reaching Earth there. This is how the communications works. Upon having to send data down to Earth, the InSight lander here, the DTN protocol will take a bundle of data that has to be sent, and it will set a time to act for it. Very much like the retransmission timeout on the terrestrial network, but it only has to make it up to the forwarding node. That's as much as the InSight lander cares about. The InSight lander sends this bundle of data up to the forwarding node, which in this case is Marco A or Marco B. Eve or Wally will send down an acknowledgement, and now the InSight lander deletes that data. It doesn't care anymore. It doesn't care if it makes it all the way to the target, because the forwarding nodes will take care of that. So now that data is sitting on Marco A or Marco B. They have drives on them, and they can hold this data. And if they need to hold this data for 2 weeks because we have solar convergence, they will do that. But then when they are in a situation where they can relay this on to somebody else, they will do that. It could be opportunistic, it could be planned. Again, they set this time to act for the bundle and then forward the bundle on to the next node in space, which acknowledges it, and then the Marco A or B will drop that data. They don't care anymore. This is set up with split horizon, so it's only going in one direction. It can't loop back around. Those of you who know split horizon from spanning tree and things like that are familiar with this idea. Then we have the Earth forwarding node that, again, sets a time to act, forwards it down to Earth, gets the acknowledgement, and now that satellite that's a forwarding node can go ahead and drop that data. It doesn't need to hold on to it. As far as InSight is concerned, it's going to assume its data makes it to that target system, just because of the nature of the way this is configured. So it's a very logical system, and it works considering the fact that we have to relay around planets, around different problems that may happen in space, solar flares, things like that. So we may have these delays, and we may have disruptions, so we can't forward at any one time. It's a beautiful store and forwarding system. Now, I teach Wireshark, and I, of course, love people to understand how the protocols work. And what's interesting is that 11 years ago, Gerald Combs, the creator of Wireshark, took a set of trace files from Vint-Cerf and built the dissectors into Wireshark. So we have the dissectors for the bundle protocol, and we already have the dissectors for the TCP convergence layer built in. So when you open up the trace files that I'm going to provide to all of you, when you open those up in Wireshark, you will be able to see the protocols dissected out and all of the different fields visible to you. A strong understanding of TCP/IP is going to be necessary for this next generation. They're going to have to understand TCP/IP really well if they want to get into space communications. And the reason is because the interplanetary internet is already here. It's already set up. And with all the projects taking place, we are going to need this next generation to support Artemis, which is our habitation of the moon, which is our ricocheting to Mars. We're going to need people that understand the communication systems to support our Mars colonization. And that is going to be this next generation. So hopefully you will be able to share some of this and excite your students on understanding communications, especially when it gets to interplanetary communications. Oh my gosh, I couldn't do that in half an hour. Sorry.
Hey, Laura, this is Mark Dempsey. Thank you so much. Anne had to step off, but she wanted me to thank you for your time, your expertise. This is great. I saw this a couple of years ago at WASC. It's a very fascinating topic. So everyone, I will get, when Laura sends me the cheat sheet, I'll make sure everybody gets a copy of that. We've recorded this session as well. We'll package that nice and neat for YouTube to share with your students or with your colleagues, so everybody can take advantage of Laura's talk here today. So thank you so much, Laura. That was great.
All right. Thanks, Mark. Appreciate it, everybody. And I will see you back over in my Wireshark class for those of you who are my students.